we started with identical particles. We are defining certain concepts. We define these exchange operators. Now the notation is somewhat will be complicated. I mean, you can think of this state as you have a particle of momentum k prime in the first ket and particle of momentum k double prime in the second ket, or usually first particle has momentum k prime, the second one has k double prime. That we will be using quite often. Now the exchange, which exchanges particle 1 and 2, so that if you apply the exchange operator on this k prime, k double prime, now the first particle has momentum k double prime, second particle has momentum k prime. This will be the terminology we will be using. And now we said that, okay, so we can define the eigenstates of this exchange operator. And so where did I? This exchange operator commutes with Hamiltonian. Now the exchange operator, you can define it as if it's acting on the states, or you can define it as if it is acting on the operators. And when it acts on the operators, basically what it does is if you have, let's say, the momentum operator of the first particle, when you act on that momentum operator of the first particle with this exchange operator, this is the action of operators on other operators. You just multiply with the operators on operator on the left and the inverse of the operator on the right. And it just exchanges, if you act on, let's say, P1, you get P2. If you act on P2, you get P1. If you act P12 on, let's say, the momentum of the third particle, if you have a third particle, it doesn't do anything. And now we said that this will be a general form of a Hamiltonian of a two-state system. And as you see, in this form at least, if you just change the operators corresponding to the first particle with the operators corresponding to the second particle, the Hamiltonian doesn't change. Basically, it tells us that the Hamiltonian and this exchange operator commute. Again, if you have two commuting operators, your eigenstates of Hamiltonian, you can always choose them to be eigenstates of this second operator. And in fact, this is not just a choice. This field theory tells us that if you have fermions, the states you have should have a negative eigenvalue under the exchange of any two particles. Now, you can just generalize it to arbitrary number of particles, but fermion states, the states of n identical fermions, they should be antisymmetric under the exchange of any two particles, and bosons have to be symmetric under the exchange of any two particles. And this is also, the definition of a fermion and boson is related to their spin. If you have an integer spin system, let me just say it's a system rather than a particle, because you can identify a composite system as a boson or a fermion also. For example, a proton, which has a total spin 1/2. Although it is not just a single particle, the proton is still a fermion, since it has spin 1/2. If you look at helium nuclei, it has two protons, two neutrons. Its spin is definitely integer, so it's a boson. Hydrogen atom as a whole is a boson. Although the proton is a fermion, the electron is a fermion, but when they combine together to have spin 0 or spin 1, forming the hydrogen atom, it is still a boson. And if you write the wave function of the hydrogen atoms, they have to be symmetric. If you have a collection of wave functions of the hydrogen atoms, then your wave function should be symmetric under the exchange of any two hydrogen atoms, antisymmetric under the exchange of any two protons, antisymmetric under the exchange of any two electrons. And then we had an example over here. Well, on Tuesday, I had forgotten to write some of the additional terms that should appear in the superposition. Now, if you look at over here, this is a 4-electron system. You can group a 4-electron system into two pairs of electrons. Each pair of electron is a boson, so you can talk about the wave function of the pair of electrons. Psi1 is one pair, psi2 is the other pair of electrons. Now, if you look at these four terms only, if you exchange psi1 and psi2, that is the exchanging the pairs of electrons. it is symmetric. If you exchange any two electrons, it is antisymmetric. So you just have to add all the remaining terms also to make sure that it is antisymmetric under the exchange of any two electrons. And then we said, okay, so if we have the symmetric and antisymmetric wave functions, what is the effect on, let's say, the probabilities? Well, this is what we had obtained for the probability of these wave functions. So this, classically speaking, what you would say is, let's say that you have d cubed r1 somewhere over here, d cubed r2 somewhere over there. The probability that you will have one particle here, another particle here, is just the product of the probabilities. You have one probability here multiplied by the other probability over there. So that's what you would get. That is the first line. But now, if they are fermions or bosons, you get the second line also. If you look at the second line, if you have the minus sign in that equation, and if you try to set R1 and R2 equal to each other, those two terms just cancel each other. So the probability of having two fermions at the same point is 0. And of course, it just doesn't go to 0 discontinuously. As they approach, their probability becomes smaller and smaller. And I should also emphasize that within this approach, at least within this simple system, there is no interaction between these particles. So these two particles are not interacting with each other. In that case, this is a solution of my system. And even though they are not interacting with each other, they still influence each other due to this statistics. And in fact, when you take statistical mechanics 501, you will actually derive an effective potential between these two non-interacting fermions or bosons. And just one more thing to note. If, for example, somehow these particles are localized in smaller regions and their separation is larger than their localization, you see that second term just becomes 0 because either some terms are 0 or the other terms are 0. You see, if psi1 is localized in some region over here, then, and if these R1 and R2 are separated points, you see psi1 R1 and psi2 R2, either one is 0 or the other one is 0. You see, this is the claim. Let's say that I have d cubed R1 somewhere over here. And I have d cubed R2 somewhere over here. And then I say that, okay, psi1, the first state is localized in this region. And psi2 is localized in this region. Which means that if the argument of psi1 is outside this region A, it's practically 0. And if the argument of psi2 is out of this region B, that is 0. Now, if you look at the second term, this multiplied by this, they're both psi1s. One is located in there, but the argument of one is in region A, the other one is region B. So that is 0. Only if these d cubed R1s are close to each other, the second term will be important. So for example, ideally, you have to anti-symmetrize if you try to write down the wave function of all the electrons in the universe, you have to anti-symmetrize the wave function with respect to exchanges of electrons in this room and the electrons in the Andromeda galaxy. But since they are so much separated, the second term will be negligible. So we can just ignore, even if you ignore this anti-symmetrization for these particles, you won't get much of a difference. And well, that was where we had left, and that is where we will be continuing. So any questions up to here? So what two electron systems do you know? Simple two electron systems.
Helium.
helium, hydrogen, whichever one you prefer. But before continuing that, let me also mention one more thing. Okay, we were writing down these wave functions. Okay, at some point we were also looking at these states. The position and momentum, spin. We have this state alpha. And then we said that what happens if we put the exchange operator here? Well, I can act the exchange operator on the left or on the right. If I act it on the left, what I will get is this is R2, M2, R1, M1, alpha. But if I act it on the left, on the right, depending on if I have fermions or bosons, this state has to be symmetric or anti-symmetric. I will get plus or minus R1, M1, R2, M2, alpha. So basically this says that even this is a general state, but even these bra and kets we have, they have to be symmetrized or anti-symmetrized. So if you identify these as the wave functions, psi alpha, R1, M1, R2, M2, this should be equal to psi plus or minus psi alpha, R2, M2, R1, M1. So these are the combined wave functions of both position and spin. And typically, these psi alphas we can write them as the superposition, if necessary, of wave functions of the form, or functions of position only multiplied by the spin. And it might happen that the psi alpha is just a superposition of not just one, but a couple of such wave functions written in this product form. And so this P12, in a sense, acting on psi alpha, we'll just exchange those things. This is how we can define P1 alpha acting on this wave function. And now you see that there we exchange both the coordinates and the spins. But that also allows us to define this the exchange operator in two parts. One is the exchanging of space. The other one is their spin. So P12 space exchanges R1 and R2. P12 spin exchanges M1 and M2 only. Which one? Because P12 acting on alpha is plus minus alpha. No, you see, alpha is a state of two fermions. It tells me that any state of two fermions or boson, if they are fermions, if you exchange in two particles, it should change sign. If it's a bosons, it shouldn't change sign. Now, let's look at these possible values of chi M1, M2. So I'm assuming that you remember something about spin addition. We are looking at electrons. So we have a plus 1 over 2, plus 1 over 2. We have two electrons. 1 over 2 M1, 1 over 2 M2. They have both total spin quantum number 1 over 2. Z component is M1 or M2. We have four combinations depending on possible values of M1 and M2. We have, let me write 1 over 2 plus 1 over 2 as plus, 1 over 2 minus 1 over 2 as minus. So the 4 possible combinations will be plus plus, plus minus, minus plus, and minus minus. Of course, these are not, the middle two at least, they are not eigenstates of total spin. So we have the total spin can be 1, and z component can be plus 1. This is the plus plus state. Then we have s is equal to 1, sz is equal to 0. This will be 1 over square root of 2 plus minus plus minus plus state. Well, this is basically just S minus acting on plus plus. And S minus is S1 minus plus S2 minus, the spin lowering operators. And then the final state with S is equal to 1 will be Sz is equal to minus 1. This is minus minus. So we have 3 states with total spin 1. These are usually called the triplet states. And then we have a single state with spin 0. Well, you see this Sz is equal to 0 states are just superpositions of those 2 states. These 2 spin states have Z component 0. One combination has total spin 1. The total spin 0 component should be orthogonal to this one because they have different eigenstates corresponding to an observable. So the orthogonal state, the state orthogonal to that combination, is just 1 over square root of 2 plus minus 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 plus. Now, if you look at these P12 operator, P12 spin, acting on a triplet state, well, all 3 of them are symmetric. This plus plus is obviously symmetric. Minus minus is also obviously symmetric. Then we have a plus minus plus minus plus. Each term is not symmetric or anti-symmetric, but that combination is a symmetric combination. So this is symmetric. It has an eigenvalue plus 1. And then the same exchange operator acting on the singlet state. You see, if you exchange plus with minus and minus with plus, the first term becomes the second term becomes the first term. Due to the relative minus sign in between, this is anti-symmetric. Well, this exchange operator, now this is amusing, let's say, can also be written in terms of observables, other observables. So let's see, P12 acting on the triplet state is that I can write it as 1 over 2, 1 plus 1. Triplet. And P12 acting on the singlet state is 1 over 2, 1 minus 3. Singlet. Now, you might be wondering what is that 1 and 3? Let me look at another operator. Let me look at S1 dot S2 operator. Well, I can write this as 1 over 2 S1 plus S2 squared minus S1 squared minus S2 squared. 1 over 2, the total spin squared, minus, well, S1 and S2, they are both spin 1 half particles, so this is h bar squared, 1 over 2 times 3 over 2 plus 3 over 2, So this is 1 over 2, the total spin squared, minus 3 over 4 h bar squared.
How does the triple combination state have a singlet state? It never becomes 0, does it? So
This is the singlet.
So I have total spin 1 over 2, which is the maximum unit.
No, the total spin can be 2. In this case, the total spin is 1.
No, but I'm talking about, all right.
I have 2 spins.
It's why 2 electrons.
I only have 2 electrons.
We started talking about 3 electrons.
Yeah. I didn't start about 3 electrons. I still have 2 electrons only. Their total spin can be 0 or 1. I have 3 states with total spin 1, that's why it's called triplet, and 1 state with total spin 0, that is singlet. So this S1 dot S2 acting on a triplet state. Well, the triplet state has total spin 1. This is 1 over 2 h bar squared 1, 1 plus 1, minus 3 over 4 h bar squared. Well, sorry, I have 2 of these, so that's 3 over 2. Which is, well, this is 2. This is 1 over 4 h bar squared. Or 4 over h bar squared S1 dot S2 acting on my triplet state just gives me my triplet state. If you like, with a coefficient 1. Now let me do the same thing for the singlet state. Singlet state has S total 0. S total acting on the singlet state just gives me 0. So I have 1 over 2 times minus 3 over 2. H bar squared, the singlet state, or minus 3 over 4 h bar squared times the singlet state, which tells me that 4 over h bar squared S1 dot S2 acting on the singlet state is minus 3 times the singlet state. So what are these plus 1 and minus 3? So let me just take those terms. Now this is equal to 1 over 2, 1 plus 4 over h bar squared S1 dot S2 acting on the triplet state, and this is 1 over 2, 1 plus 4 over h bar squared S1 dot S2 acting on the singlet state. So triplet states and the singlet states are all my states available. So those two operators act in the same way in all my base states, so they are equal. No. S1 dot S2 doesn't change the total spin.
No, not S1 and S2, but singlet state eventually kind of became a triplet state. Right?
Where? No.
I added the P1 to spin to the triplet state, and I ended up with a triplet state.
No. Exchange doesn't change the total spin. And S1, S2 doesn't change the total spin. Other questions? So let's go back to our wave function. You see, we have this factorization of the wave function in terms of spin degrees of freedom and the space degrees of freedom. And I know that psi alpha for electrons, we are looking at the electrons. If we are looking at the electrons, let's say. If chi is one of the is a triplet, phi r1 r2 should be equal to minus phi r2 r1. And if chi is a singlet, then phi r1 r2 should be equal to plus phi r2 r1. The wave function, the space wave function of the electrons can be symmetric or can be anti-symmetric. The space part doesn't have to be anti-symmetric. But the thing is, the total wave function has to be anti-symmetric. And the total wave function has the space part and the spin part. So if the spin part is anti-symmetric, the space part has to be symmetric, and vice versa. Now, another consequence of this one is, you see this phi r1, r2. You can write it, you can also factorize this in terms of the motion of the center of mass. And the relative separation here, capital R is R1 plus R2 over 2, and small r is, let's say, R2 minus R1. If you have a two-body problem, you can always separate the center of mass motion from the relative motion. Now, this exchange of particles, which exchanges R1 and R2, it doesn't change the center of mass position, but it just reverses the relative position. This is how the P1 space, let's say, acts on this space wave function. Now, let's remember a bit of quantum mechanics from undergraduate. If you have, let's say, a spherical symmetric potential, you can separate your wave functions in terms of spherical harmonics and the radial parts. And when you change r to minus r, r goes to minus r in spherical coordinates, distance from the origin doesn't change. It's the same. Well, theta goes to pi minus theta. Sorry, this is theta. This is the angle from the z-axis. Angle the position makes with the z-axis, and phi goes to pi plus phi. What these two does is y lm omega goes to minus 1 to the power l y lm of omega. So what does this tell me? Well, the space part, the wave function of the space part, the space part of the wave function of these two electron systems, their symmetry or anti-symmetry is determined by their angular momentum. If they have an odd angular momentum, then the wave function is anti-symmetric. If they have even angular momentum, the wave function is symmetric. So what do we have? If the two electrons have total spin is equal to 1. This is a symmetric spin wave function. So space part should be anti-symmetric. But for space part to be anti-symmetric, L should be odd. They cannot have all the angular momentum. They have to have an odd angular momentum quantum number. And if the two electrons have total spin 0, the spin wave function is anti-symmetric, so the space wave function should be symmetric, but that means L should be even.
Can you repeat the last sentence?
S is equal to 0.
Yes.
You see, if S is equal to 0, the wave function, the space part of the wave function is this one. But if you look at that one, that is an anti-symmetric wave function under the exchange of spins. Now, the total wave function is a product of the space part and the spin part. The total wave function for electrons, it has to be anti-symmetric. I have to take the minus sign for electrons. Well, if the spin part is anti-symmetric for total spin 0, the space part should be symmetric. Now, the space part, the symmetry of the space part is given by minus 1 to the L. So minus 1 to the L in all the terms appearing in that sum should be even. It should be 1, minus 1 to the L should be plus 1. That means only even L terms can appear in that sum. So that is what I mentioned over here. Again, I underline here, this is true even if there are no spin-spin interactions. In fact, even if there are no interactions between those two electrons, even if the electrons are not interacting with each other in any way whatsoever, their spin determines the possible values of angular momentum because of this statistics.
Orbitals we see in the chemistry courses like SPDF and there's electron numbers. Are they a result of this?
We will come to that. We will look at the helium atom, for example.
This implies something else. For an harmonic oscillator, we have parity-even and parity-odd solutions, right?
Mm-hmm.
So this implies that some of them have an even angular momentum and some of them have an odd angular momentum. But how will I calculate the odd angular momentum? I always assumed that it was 0 in the past, but...
Well, what is the problem? You have a single particle, single harmonic oscillator, then you cannot talk about exchanges. So what are we talking about? The wave function, I mean, here we are talking about the symmetry under the exchange of any two particles. So you have to have, if you want to somehow use these concepts, you have to have more than one particle. But let's say that you have a hydrogen molecule. So you have a hydrogen molecule-like system, let's say. You have 2 point particles connected by a harmonic potential. So if you go to the center of mass motion and the relative motion coordinates, you will see that the center of mass is just the motion of a free particle. Here m is 2m, mu is m over 2. The reduced mass. So this will be your system. Now if you write the solutions, the eigenstates, well, there will be one overall translation, which depends only on R, which will be, you can take it to be a plane wave if you like. And there is the relative motion. which will the relative wave function, which will depend on R. In principle, ignore any statistics. The relative motion will be something like some coefficient e to power minus r squared with certain coefficients. And what were the polynomials? Harmonic polynomials. And you also have YLM. So this will be the general solution. And in principle, you can say that, oh, L can take any value. Now, if these two particles that we are talking about are, well, this is the Hamiltonian, they are identical, L cannot take any value. For example, if they are electrons, we have two electrons, somehow there is an effective harmonic potential created between them. In that case, their total spin can be 0 or 1, and we still have this condition. If the total spin of those two electrons is equal to 1, then only odd values of L are allowed. If the total spin is 0, only even values of L are allowed.
What is the field that is quantizing spins?
What do you mean by quantization?
Why can it only take 1 over 2, 1 over 3 over 2, etc.? Can it be 1 over pi?
Which one?
The spin, any
No.
spin of some object. Why?
That's what the experiment tells us. We have no idea why. The spin is quantized. Well, we have no idea why. We have a mathematical idea why. It's the properties of the rotation group. But that's all we know. And in fact, if you go to 2 dimensions, the spin can have any value. In less than 3 dimensions, in 2 dimensions, the spin can have any value. It's called anyons, if any one of you are interested. Anyway, if you go back to our simple, commonly known electrons, our common electrons, so this is what will happen if you have a harmonic, if you create a harmonic coupling between 2 electrons.
So what's the spin for anyons?
Can be take any value. They are not quantized.
So they're not quantized.
The spin of anyons are not quantized.
I was going to ask, is there something else? Is there some other class of particles which obey exclusion principle? Because we have composite particles in condensed matter all the time, right? But I don't know anyone that has a Pauli exclusion principle type.
All the quasi-particles, if they are fermions, they obey the exclusion principle.
So Cooper pairs?
Cooper pairs are bosons.
Right, okay. So what is an example of a fermionic quasi-particle?
Proton, not a quasi-particle, but a compound object.
I mean, quasi-particle in the condensed matter sense, like
I don't really know.
I don't.
The electron, quasi-electron, the dressed electron, is still a fermion.
So the spin statistics theorem doesn't say anything about an exclusion principle, right?
What do you mean? Well, spin statistics theorem, at least in higher than 2 dimensionals, tells me that if you have fermions, the wave function of the fermions has to be antisymmetric under the exchange. Pauli exclusion principle is a direct consequence of this antisymmetry.
Also, something I meant to ask last time. The spin statistics theorem is dimension independent?
No, in 2 dimensions it doesn't hold.
I mean, higher than 3.
Higher than 3, yes.
And we know that it's provable, or we just.
Well, you see, the proof, we will study, for example, the Dirac equation, relativistic equations. The proof is basically based on the fact that if you have fermions, their equation of motion is linear in time. Bosons, their equation of motion is second order in time. That makes the difference.
Okay, I don't know if you know, there's a result by Boyer and Sudarshan that said that there's in 8D, I think, or 4D, the spin statistics theory that doesn't hold or has a different.
I don't know.
Okay, sure.
Any other questions about our common electrons in our common three-dimensional space? Okay, so let's look at let's start looking at the helium atom. Well, helium is we have a heavy nucleus with the common helium is 2 protons, 2 neutrons, which is very heavy, and there are 2 electrons around. So we can treat the nuclei as fixed. So the Hamiltonian, well, it will practically have this form with a different potential, of course. P1 squared over 2m plus P2 squared over 2m. Then we have the attraction, the potential energy between the electron and the nuclei minus ZE squared over R1 minus ZE squared over R2. And then we have the interaction between the 2 electrons. We have E squared over R12. R1 being the length of the distance of the first electron from the nuclei, R2 is the second one, and R12 is their separation. Now, if the last term were absent there, let me define an HI to be minus ZE squared over Ri. So the total Hamiltonian is H1 plus H2 plus, let me add the V. V, I'm calling this one V. Well, I will be using some perturbation theory to study this system. This will be my H0, the unperturbed system. This is my perturbation, if you like. Now, H0 has this property that H0 is the sum of 2 independent systems. So I can straight away write down the solution. Psi will be psi 1 of R1, psi 2 of R2. But now I have to symmetrize this or anti-symmetrize this. Let me write a plus or minus psi 1 of R2, psi 2 of R1. Of course, if psi 1 and psi 2, if they are the same, they cannot be the same state. Yeah, okay, yeah. Well, I'm separating out the spin part, so that there will be also a spin part. But since I don't have any spin-spin interactions over here, I'm omitting to write down the spin part. But in symmetrization, I have to keep that in mind. So if I have a total spin 0 state of these 2 electrons, in that case, I have to pick up the minus sign, and psi 1 and psi 2, they have to be different. If I have this symmetric triplet state in the spins, then if I have the triplet state, then this has to be anti-symmetric. If I have the singlet state, this has to be symmetric. In that case, I have the plus sign over here. If I have the plus sign, psi 1 and psi 2 in principle can be the same. If psi 1 and psi 2, they are the same, then I don't have that 1 over square root of 2. Okay, let's assume that, let's start with the ground state. Then this psi I of Ri will actually be just, let's say, psi 1, 0, 0. In fact, their explicit form is some coefficient times e to power minus zr over a0 being the Bohr radius. This is the only dependence they have. So psi g, let's say g for the ground state, will be psi 1, 0, 0, psi 1, 0, 0, R2. Now the energy of this state let's say the zeroth order energy, will be, well, if it was a hydrogen atom, the ground state has energy minus 13.7 electron volts. Now here I have Z is equal to 2. The energy has a Z squared dependence, so I have a 2 squared. And then I have 2 electrons having this energy. So this is something around 100 electron volts.
Is this the case that they are separated enough to not interact with each other?
No, I'm just, to a zeroth order approximation, I'm ignoring all the interactions between these 2 electrons. Now, how good an approximation that is, it's another issue. We will come to that. We will calculate the corrections. Let me pick up. Well, this is 108. Now, the experimental value is 79. So not such a great approximation.
Hocam ben şey anlamadım. 2'nin karesiyle mi geçiyor? Evet. Ha.
That is Z squared, for Z is equal to 2. Now the first correction, due to this perturbation. So how do you calculate the first correction? To the energy. Yeah. It's just the expectation value of V. Or E squared. Now the question is how to calculate this. We know the wave function. So 1 over R1 minus R2 will have a complicated expansion. In fact, you can write this as 1 over square root of R1 squared plus R2 squared minus twice R1 R2 cosine gamma. Gamma being the angle between those 2 vectors R1 and R2. So I'm assuming you have all taken the electromagnetism course. If you don't remember the multiple expansion, this is the electrostatic potential of the point charge. So you study this in detail in electromagnetism, especially in doing the multiple expansion. This is equal to sum over all L of the smaller among those things over L divided by the larger one among R1 and R2, L plus 1 Legendre polynomial of cosine gamma. In fact, this is called, that factor on the left is called the generating function of Legendre polynomials. You just make a Taylor expansion in R small over R large. Well, R small is equal to the minimum of R1 and R2. R large is the maximum. And you can in fact go one step further. This is equal to Lm, R small to the L, R large to the L plus 1, 4 pi over 2L plus 1, YLm star omega 1, YLm omega 2. This is the expansion you use to show that any potential has a multiple expansion. Omega 1 is theta 1 phi 1, the angular coordinates of R1. Omega 2 is theta 2 phi 2, the angular coordinates of the other one. Hmm?
YLM gamma, something dependent on
Well, you see,
gamma.
this is the expansion we have. Cosine gamma is equal to 4 pi over 2L plus 1 summed over m y L m star omega 1.
But now these are the integration variables. Gamma dependent on the integration variables.
Gamma depends on theta 1, theta 2, phi 1, and phi 2. So if you just expand it, you see, gamma is a function of theta 2 and phi 2. YLMs are a complete set. So since PL of cosine gamma is a function of theta 2 and phi 2, I can expand PL of cosine gamma in terms of YLM omega 2. That exists. What are the coefficients? Well, that's a different problem, but the coefficients will depend on theta 1 and phi 1, which turns out to be also spherical harmonics. Well, the way to prove this, well, effectively we have this identity. Well, the left-hand side is nothing but the potential created by a point charge located at the point R2, and this is the potential created at the point R1. We know that the potential satisfies the Poisson equation. You can go ahead and try to solve the Poisson equation in spherical coordinates. That will give you the right-hand side. But you know that the potential of a point charge is unique. It might look different, but whatever expression you have, they have to be equal to each other. So that proves that the two sides are equal to each other. I do advise you to go over that exercise so that you will also review electromagnets and special functions course. Now let me just write a couple of more steps. You see, eventually I wanted to calculate that one. And that integral you see, this is d cubed R1, d cubed R2, 1 over R1 minus R2 times psi g of R1, R2 squared. Then some normalization factor exponent minus twice z R1 plus R2 divided by A0. Right, this is not a trivial integral to evaluate in this form, because that 1 over absolute value of R1, R2 has a complicated dependence on theta 1, theta 2, phi 1, and phi 2. But if you use this expansion, that integral becomes sum over Lm. There's a normalization factor, d cubed R1, d cubed R2, R small to the power L, R large to the power L plus 1, and I have the exponent and then I have YLM star omega 1, YLM omega 2. Now the angles are separated. They're just written as products inside that integral, so I can evaluate theta 1 phi 1 integral independent of theta 2 phi 2 integral. And the omega, YLM omega, this is actually square root of 4 pi Kronecker delta L0, Kronecker delta M0. So although here I have a summation over L and M, only one term contributes to that integral. So this psi g 1 over R12 psi g turns out to be some coefficient. I'm not writing the normalization coefficient, you can just look it up. Let me write this in terms of the radial part, R1 squared dr1, R2 squared dr2. Then I have the smaller one to the power 0 divided by the larger one to the power 1 because L is equal to 0. I have the exponent minus 2z R1 plus R2 over A0. And that's it. Now I just need to take the radial integrals. And for that also you have to, okay, then this overall constant R1 squared dr1, R1 goes from 0 to infinity. Well, let's separate the R2 integral from 0 to R1. Within this integral, R2 is smaller than R1. So I have this R small is R2, R2 to the power 0 divided by R1 to the power 1. Then I have the integral from 0 to R1 to infinity, dr2 R2 squared. Now the small one now is R1 times the exponent, which I will not evaluate, I will just write the result. The shift is 5 over 2 e squared over 2a0, and the first order energy up to first order corrections just turns out to be minus 74.8 electron volt. Exact value is 79. Well, we are approaching. You see, the correction is almost 30%. The first order term is large. So I wouldn't stop here since the first order term is already not very small. You should probably calculate the second order correction to the energy and see whether it is small or not. Now, any questions? Now, we can do better than this. We will do better than this in the helium atom. Let's give our 10-minute break now, and then we will continue.